afternoon. I am Renu Sharma, Assistant Professor, EC Department. Today, I am going to start with the next topic of this subject, that is wireless and mobile communication. The topic of today's lecture is channel modeling. So, in case of wireless and mobile communication, the channel that we consider for the purpose of transmission of information, it is wireless in nature, because it is the signal is broadcasted, there is no direct connection is set up between the transmitter and receiver. It means there is not always possible that there exists a line of sight between the transmitter and receiver, because it will go under multipath propagation is there. So, various propagation effects are there which will going to change the characteristics of the signal, and that is known as multipath propagation. So, in this channel modeling, we will going to discuss the topic, that is introduction of what is channel modeling, how we are going to model the channel, then propagation mechanism, channel effects. There are various effects that will going to change the characteristics of the signal that will travel over the channel, then multipath scenario will be there, and then free space propagation mechanism, where we are going to derive an equation for the power that has been received at the receiver after undergoing various losses and various parameters, like it will going to constitute the gain of the transmitter antenna, gain of the receiver antenna. So, there are various parameters that will be used to calculate the received power. So, first we will begin with introduction. So, a wireless channel is basically, it is a dielectric unguided medium that can be analyzed in the following different ways. So, what are the different ways? Like first we will discuss what is unguided. Unguided means there is no direct connection set up between the transmitter and receiver. It is the wave which will be going to travel from the transmitter. It is unguided in nature, which means we have to guide. It has to decide at every hop or at every intermediate node that where it has to move on, depending on the path length, depending on the idealness of the channel. So, that is known as the unguided medium. So, there are three different ways in which we can model a channel that is an unguided medium. Like first one, by using the fundamentals of electromagnetic wave theory, that is phase velocity, phase propagation constant, amplitude, frequency and phase. So, the first characteristics or the first type by which we can model a channel is by using the electromagnetic wave theory fundamentals, where we can consider parameters like amplitude, phase and frequency of the signal which has to travel from transmitter to receiver. Also, we can use this phase velocity, then phase propagation constant, which is directly related to the electromagnetic spectrum. Now, second is by using the ray theory, reflective index dependence, then reflection scattering. These are the four parameters that will going to change the characteristics of the signal in multipath propagation. So, that is a part of ray theory, because in case of ray theory, if you remember, like this is a medium, this is medium 1 having refractive index n 1, this is medium n 2 having refractive index n 2. So, let us say this is a wave which will going to travel from one medium to another, either it will be going to travel towards this normalization, or it will going to travel to this, means the change of medium from one medium, the travel or the wave will travel from one medium to another medium. So, that is known as the refraction. So, it is also undergoes the total internal reflection also, that is TIR. So, that is related to the ray theory. Now, next is third one is by using the fundamentals of digital signal processing, like such as the channel transfer function, spectrum, channel impulse response, convolution with the transmitting signal. So, this is the third one which we are going to see here, which we are going to discuss, that how the channel will be modeled using convolution. So, in this case, in the third case, what we are doing, let us say this is a transmitter and this is a receiver. The signal will transfer from transmitter to receiver over a channel. Then at the channel, what is there? There will be a AWGN noise will be there, because in this communication we are using, we are considering the AWGN noise most of the time, because when we are doing the mathematical analysis of this particular noise, its transformation and inverse transformation is same. It is like the Gaussian function and it is additive in nature. So, that is why we can easily do the mathematical representation of this noise, and its PDF, that is power spectral density PST, will be constant from minus infinity to infinity, that is denoted by N naught by 2. So, this is the transmitter, this is the receiver. Let us say here a signal xt which will going to travel over the channel, and there will be an effect of noise, that is denoted by Nt. It will be modulo 2 added with this particular signal, and then it is received at the receiver side. So, this is denoted by Yt. So, this is the signal which will travel from the transmitter to the receiver. So, by using this fundamental of the digital signal processing, there will be a channel transfer function, channel impulse response will be there, and we are going to convolute the input signal with the channel, the signal that will be going to affect the signal at the channel, that is the noise only. Now, next is propagation mechanism, where we are going to see some of the definitions that is related to the wireless mobile communication. Like first one is line of sight. Now, line of sight is basically is the wave propagation in which the electromagnetic ray follow a straight line from the transmitter to the receiver. So, in the next figure these 5 definitions are explained very well. Line of sight means there is no noise, or you cannot say noise exactly, noise will be there whether it is line of sight or no, there is no line of sight. Line of sight means when there is no intermediate hop exist between the transmitter and receiver. The signal will going to travel from the transmitter to receiver directly. It can directly visualize that what is the path of the between the transmitter and the receiver. So, that is known as the line of sight. There is no tree exist between the transmitter and receiver, no building will be there, or no intermediate node exist between the transmitter and receiver. So, what are the advantages of this line of sight? The direct advantage is that when there is no intermediate hop exist between the transmitter and receiver, then the strength of the signal from the till the point it will be received at the receiver, it will be maintained, it will not going to degrade, because there is no hop exist between the transmitter and receiver. And also since the strength of the signal will be maintained, so there is no chance of retransmission required, because there is no loss that will going to change the reduce the energy of the signal or change the characteristics of the signal. So, that is why this line of sight is very important, that practically it is possible only in open areas. It is not possible in suburban or urban areas where the population is quite large and there are large number of intermediate nodes exist, like there will be trees will be there, high rise buildings will be there, and in case of open areas also like farm field, there exists line of sight, but the areas like the hilly areas, hill may be there as an obstacle, as is a countable obstacle that will exist between the transmitter and receiver. So, in open areas and especially in the field areas, it is possible to have the visualize the line of sight. Second one is the non-line of sight, that is denoted by NLOS, that is based on a resultant mechanism. Now, what is non-line of sight? So, I have said that when there exists some intermediate node or some obstacle between the transmitter and receiver, then there is no line of sight exist. So, how the signal will undergo under this condition. So, there will be 4 parameters, like first one is the reflection, second is diffraction, scattering and refraction. So, in case of this reflection, this occurs when the propagating wave impinges on an object that is larger than its wavelength, which means let us say I have transmitted a signal having frequency 200 hertz. Now, you can calculate the wavelength of 200 hertz by using the formula lambda is equals to c by f. C is the speed of light, like this is the formula, lambda will be is equals to c by f, c is the 3 into 10 to the power 8 meter per second, f is the frequency, let us say I have taken 200 hertz, then you can calculate the lambda. So, after calculating the value of lambda for that particular incident wave, then if that if the wave impinges on an object which is having whose size is larger than its the wavelength, that is lambda that you have calculated, then the signal undergoes reflection. Example of such objects are the surface of earth, building and walls, which has a huge area, which has its size is quite large as compared to the wavelength. Second one is the diffraction. Diffraction is occurs when the radio path between the transmitter and receiver is obstructed by a surface which has sharp irregular edges, like the edge of a wall, the edge of a building, the edge of a hilly area. So, that is known as a diffraction. So, which results in waves bending around the obstacles. Now, diffraction is more with low frequency signals than the high frequency signal. Why is it so? Because in case of low frequency signal, the lambda is quite high and it will going to affect the quality of the signal quite much more. It will going to affect the quality of the signal when it impinges on a sharp object. Third one is the scattering. This occurs when the propagating wave is obstructed by objects that are smaller than the wavelength. Now, you can see that what is the difference between reflection and scattering. In case of reflection, when the object is quite large as compared to the wavelength, and in case of scattering, when the object is smaller than its wavelength. The example of scattering is lamp post, foliage or street sign and particle in the air. So, that means size of the object is very small as compared to the wavelength of the signal which it will going to impinge. Now, next one is the refraction. Due to the variations in the refractive index of the atmospheric layer, the electromagnetic wave bends. So, that is known as the refraction. This is due to the different layer, like troposphere will be there, stratosphere will be there. So, as the number of layers are there quite large in case of atmospheric layer. So, that signal will going to refract. So, this is the diagram which is showing all the 4 different examples. Line of sight will also be there, like this is an obstacle, this is a building, you can see a sharp edge exist. This is the signal from the elevated base station. So, you can say that this is the transmitter and this will be, this is also a transmitter and this will be a receiver. So, there is direct line of sight exist between this transmitter and receiver, and there is no direct of light of sight does not exist between the transmitter and receiver. This is the scattering part, this is mobile receiver. So, this is how this is the reflected signal. So, this diagram is basically showing all the 4 different options. Now, next is the channel effects. So, when we are modeling any channel, modeling means we have to derive an equation, we have to design a channel which is wireless in nature, which is unguided, and we have to design depending on some of the different probability density functions like Rayleigh probability density function or region distribution. So, these are the different probability density functions that we have to consider to design a particular channel. There will be 2 different types of modeling are there, like indoor channel modeling and outdoor channel modeling. In case of indoor, we do not have to consider any obstacles like the hilly areas, trees and all. In case of outdoor, we have to calculate all these conditions. We have to see that what will be the height of the transmitter, what will be the height of the receiver, what is the distance between the transmitter and receiver. Because in case of outdoor cases, there is high chance of non line of sight, and different obstacles will going to affect the quality of the signal. So, that is known as the outdoor channel modeling. Example of outdoor channel modeling is Okumura model, Hata model, which we are going to discuss in the coming lectures, the different modeling. And there is also indoor models, example are the Rayleigh distribution, region distribution. So, these are the examples of indoor modeling. So, channel effects means what we are going to see is how the channel quality of the signal will going to degrade when it travel from the transmitter to receiver. Like first one is the attenuation, it is the drop in the signal power when it is being transmitted from one point to another point. So, it is caused by the transmission path length obstructions in the signal path and multipath effect. So, whenever the signal will travel from the transmitter to receiver, there will be different signal powers which will going to degrade the quality of the signal, which will going to change the characteristics of the signal, which is known as attenuation. The signal is attenuated. When you heard about this line that signal is attenuated, means the strength of the signal or the power of the signal gets reduced due to multipath propagation, because multiple effects are there, like the atmospheric propagation will be there, or raindrop is also there, which will change the characteristics of the signal. Next one is the fading. So, as there are obstacles and reflectors in the wireless propagation channel, the transmitted signals arrive at the receiver from various directions over multiple paths. Such a phenomenon is known as multipath. So, let us say this is a transmitter, this is a receiver, this is a tree, you can say this is a tree, this is a building, and this is a car, moving car is there. These two are static in nature, this is moving in nature. So, let us say a signal will be transmitted, it will going to impinge on this signal, then it will going to impinge on this signal, this one and this one. So, you can see some of the signal will be received from here, some of the signal will be received from here, some. So, you have to add these 4 different signals, because at the transmitter you have transmitted only single signal, and due to the multipath propagation it has undergone different multipath. So, these 4 signals which you have received, you have to add it together. So, that is known as multipath propagation, where different signal will be added. So, fading is the result of multipath in which the signal strength varies continuously with respect to the distance and with time from the transmitter to the receiver, along with the attenuation. So, attenuation is also counted in this fading, where in multipath propagation the signal strength will be reduced, and it will be calculated by adding different signals which are received from different paths. Next one is shadowing. This occurs when there is an obstruction between the transmitter and receiver, and it can be observed in long distance communication as well as short distance also. It is generally caused by building and hills. So, shadowing is also a kind of channel effect which is possible in multipath propagation. Now, this is the multipath scenario. This diagram is showing multipath scenario. Now, you can see that this is a mobile receiver which is moving in nature. It is not static. This is hill, and this is the direct ray that will be exist from here to here, but this is ray 1, ray 2 and ray 3. Now, you can see that this is impinges from means it is reflected from a building, it is reflected from hill, it is reflected from another path, and this has been received by the receiver. So, this undergoes multipath propagation. This is the multipath scenario, which is very normal in case of urban areas, suburban areas. Now, next is the free space propagation scenario. Now, what is free space propagation? You can say model also. In this case, free space propagation model, we have to visualize a model which is been used to calculate the power received at the receiver side. So, that formula that you are going to calculate, we are going to calculate is denoted by PR. We have to calculate the received power, and that formula is known as Friss formula. This is known as Friss formula. Now, Friss formula is basically a kind of formula that is used to calculate the received power. It is also used to calculate the effective temperature of a particular device of amplifiers. It is used to calculate the amplifier aperture amplifier power also. So, that is a effective temperature TE for different amplifiers which are connected in cascade. So, Friss formula is not specifically for PR, it will be used for TE also. So, free space model is a valid only for values of D that are in far field of transmitting and less than the radio horizon. So, this Friss free formula model for calculating this particular model, To calculate the value of PR, we have to consider an isotropic radiator. Isotropic radiator is nothing, it is an antenna which is omnidirectional antenna, which is an isotropic in nature, and its gain is equals to 1. So, that is known as an isotropic radiator. So, isotropic radiator, its radiation pattern is denoted by a sphere, which means it will be installed in a cell at the center of the cell, and it will going to radiate the information equally in every direction. So, that is the free space that is used for the free space propagation model. So, ideally we are going to consider this then, because when we are using this particular model for the mathematical calculation, its gain will be is equals to 1. Then this is an isotropic radiator which will going to radiate equally in every direction. This is the receive antenna aperture. Now, this is near field, this is far field, this is Fresnel zone, this is Fraunhofer region, and Fraunhofer region is calculated by 2d square upon lambda. This is the formula, where d is the distance between the transmitter and receiver, lambda is the wavelength of the signal which has been transmitted, RF is the Fraunhofer region. So, this is the formula. Now, we are going to calculate the formula for received power. So, we have to consider an isotropic source of transmitter, which may be half wave dipole antenna. Half wave dipole antenna means its length will be equals to lambda by 4. The flux density at a distance d can be calculated by P t upon 4 pi d square, its unit is watt per meter square. Now, here we have considered the isotropic radiator or the isotropic source. So, gain will be in this case G will be equals to 1, but when we are going to consider an antenna with an effective isotropic radiated power, that is denoted by P t into G t, then the flux density is calculated by P t into G t divided by 4 pi d square. Here G t will be equals to 1, but since we are considering an antenna with which is directive in nature, its gain is having some value, then it is P t G t divided by 4 pi d square. Now, the power P r received by the receiver antenna with an area A r is equals to flux power density multiplied by the area of the receiver antenna that receives the flux density, which is denoted by F into mu A r watts. Now, where eta A r is equals to A e, that is the effective area of the receiving antenna, and eta is nothing, it is the antenna aperture efficiency. So, this is the formula which is used to calculate the PR. Now, we have to put the value of AE here. So, PR will be equals to PT GT AE upon 4 pi d square. Now, receiving the antenna gain which we are going to calculate, this is the receiver antenna gain 4 pi E AE upon lambda square, then PR will be equals to lambda square upon 4 pi d square GT PT into GR. So, this is how you have to calculate the value, and lambda will be equals to C by if you know. So, it can be replaced by this formula also. So, PR will be equals to PT GT GR lambda square upon 4 pi d whole square multiplied by L also. So, this is the Friss formula. Here L, if it is given, this is going to constitute the system losses. System loss and attenuation and other losses are different. If system loss in numerical it is given, then you have to consider its value, then otherwise it has to be L will be equals to 1 when we are talking about the numerical part. Then lambda square upon 4 pi d square, it is nothing, it is the path loss. P t into G t is the EIRP, that is the effective isotropic radiated power. Now, this is the path loss formula. You can see that this is PL dB, which is equals to 10 log transmitted power upon received power, that can also be written as this one. So, you can see what I have told you, that the path loss in terms of decibel, it is lambda square upon 4 pi d whole square. Minus is required because it is originally it is 4 pi d upon lambda square. So, you can see from here also that what I have written, this is the Friss formula, and if it is L is given in the numerical, you have to consider, otherwise it will be calculated as 1. Next one is the noise parameters. Since we have discussed initially that how the channel has to be modeled, in this lecture we have not discussed about what are the different models that exist for modeling a particular channel. We have seen that how the channel has to be modeled. So, different noise parameters are there which will be calculated, which has to be calculated while designing a model. Like first one is the noise factor. For components such as resistors, it is the ratio of the noise produced by the real resistor to the simple thermal noise of an ideal resistor. So, f noise will be is equals to signal to noise ratio at the input divided by signal to noise ratio at the output. Noise figure, it is also known as figure of merit. Noise figure is the noise factor converted to decimal notation. Now, NF will be is equals to, if you are converting noise into decibel, then that is known as the noise figure. Other one is the noise temperature. Now, noise temperature is also known as the Friss formula, that is for the effective temperature of the system. So, it is the means for specifying the noise in terms of an equivalent temperature. This is the formula which require the noise figure. So, T E equivalent temperature is equals to F noise minus 1 into T naught. T naught is nothing, it is the room temperature at 300 degree Kelvin or 27 degree Celsius. So, this is how you have to calculate the T E value. So, these are some of the parameters. So, in this lecture we have discussed about different channel model, how to model a channel, what is the effect of noise, what are the different parameters that will going to change the characteristics of the signal. Then we have discussed this noise parameters also, and a very important equation we have derived, that is known as Friss formula. These are the references that you can consider for this particular topic. Thank you.